Hello and welcome back. Let's finish up looking at antiderivatives in this video. We had just looked at antiderivatives of exponentials, done a few examples. So the next obvious thing to do is to look at antiderivatives involving natural logs. So when we take the derivative of a natural log, this was one of the easiest logarithms to take the derivative of. This is just going to be 1 divided by x. So that means that if I take the antiderivative of 1 over x, I should get a natural log, right? So, because the antiderivative should just go backwards. So I do want to get the natural log of x, and I can't forget my plus c. There is a caveat here, though, and this is because we can't take the natural log of a negative number, or even 0. Well, I can't plug 0 into 1 over x, so x here couldn't be 0 to begin with anyway, but I could take, but this could involve negative values of x. So since I can't take the natural log of negative values of x, what we do is we add absolute value signs around here. And I apologize, the way I write natural logs, it's maybe a little bit confusing with the absolute value signs here, but this is for all values of x. Now, if we were told to begin with that x is positive, so let's say that here x is only positive, then I don't have to worry about these absolute value signs, and I can just say, oh, it's just going to be the natural log of x, and again, plus my constant out the back. So, yeah, we do have to be a little bit careful with natural logs. We can only take natural logs of positive numbers, so we need the absolute value signs when x could be anything. But if we know ahead of time that x is positive, then we don't really have to worry about it because the absolute value of positive numbers is just themselves. So let's just do a couple of examples. So here we've got the antiderivative of 2 over x dx. So again, I can pull out the 2, and then I've got the antiderivative of, I started writing the answer instead of the question, 1 over x dx. So this is just going to be 2 times the natural log of x, and I can't forget my absolute value signs. Also, plus c. Can't forget that either. So let's finish up with one last question. I want to take the antiderivative of x squared plus x plus 1 plus 1 over x plus 1 over x x squared. Let's do one big final antiderivative. So I've got the antiderivative of each one individually. So rather than writing all that out, I'll just say that out loud. So the antiderivative of x squared. Well, this is just a power of x. So this is going to be x to the 1 higher power divided by that power. The antiderivative of x is going to be x to the 1 higher power. Well, 1 higher than 1 is 2 divided by 2. The antiderivative of 1, this is just going to be x. Again, we can think about 1 as x to the 0 power, and we can go through the motions like that. Or we can think, if we take an antiderivative of a constant, it's just x times that constant. Then I have the antiderivative of 1 over x, which we just learned is the natural log of x with the absolute value signs in there, because we can't take natural logs of negative numbers. And then here I've got 1 over x squared, which is the same thing as same thing as x to the negative 2. So 1 bigger than negative 2 is negative 1, and I need to divide by that negative 1. So simplifying, there isn't a whole lot to simplify here, except for this last guy. 1 divided by negative 1, that's just negative 1, and negative 1 times x to the negative 1 power. I'll just write that as 1 over x. And again, once we take the antiderivative, we can't forget our plus c. Very, 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 very important. And I will guarantee that you will forget, and you'll forget a couple of times, and by the third time, you will have been reminded enough that you won't forget it anymore. So this has just been a fairly quick introduction to how to take antiderivatives. It's just undoing derivatives. And one application for this, or one way that we might apply this, is in the following sense. So here we'll do two final questions in this section. Here I want to find a function. I want to find an f of x whose derivative is x squared plus x, and if I plug in a 0, I get 2. So let's think about this. If I want a function whose derivative is this guy, I need to undo that derivative to find the original guy. So I need to take the antiderivative. So let's take the antiderivative of the derivative to find my original function. So this is going to be the antiderivative of x squared plus x, and the antiderivative of x squared is just like in the last question. X squared, we raise it to the 1 higher power, and we divide by that power. X is just x to the first power, so raise it to the 1 higher power and divide by that power, plus c. Ooh, well, plus this I don't know what this constant is. So my f here, this is going to be my f of x. So f here is going to be 1/3 x cubed plus 1/2 x squared plus c, but I don't know what c is. C is just some arbitrary constant at this point. But we're told enough information that we can figure it out. We're told that f of 0 is 2. So that means if I plug a 0 into here, I should get 2. So what is f of 0? Well, if I plug a 0 in here, I get 1/3 times 0 cubed plus 1/2 times 0 squared plus c. And 1/3 of 0 cubed is 0, 1/2 of 0 cubed, 0 squared is 0. So 0 plus 0 plus c, well, that's just c. And I know that all that has to be equal to 2. So ultimately, my function is going to be 1/3 x cubed plus 1/2 x squared plus 2. I was able to figure out what c was by plugging in this guy. These are called initial conditions. Initial conditions essentially describe what our function looks like at the start. Now, at the start can be used to mean a few different things. Essentially, what this amounts to is that using the antiderivative, we see that we get this extra constant in here, but with a little bit extra information, knowing one value of our function, in fact, lets us find that c. And we can do one more quick example here. So find an f of x such that the derivative of that function is 1 over x plus 2 over x squared. But we're also told that f of 3 is equal to 0. So even though we have to take the antiderivative here to find out our original f and we get a constant, we have enough information to figure out that constant. So again, we know that f, the antiderivative and the derivative should cancel out. So if I take the antiderivative of the derivative, I should get back to f. So here, this is going to be the antiderivative of 1 over x plus 2 over x squared. And then again, I have the antiderivative of 1 over x, which we just learned is going to be the natural log of the absolute value of x. And then we have 2 over x squared. So I can pull out the 2 first, and then I have 1 over x squared, which is the same thing as x to the negative 2. So raising that to the 1 higher power, so 1 more than negative 2 is negative 1. And then I need to divide by that power, and then add c. So this is going to be the natural log of the absolute value of x. Maybe I should try to make that a little bit shorter. So the natural log of the absolute value of x plus, well, it's not even going to be plus because I've got a negative sign. This is 2 times 1 divided by negative 1. Well, that's just negative 2. X to the negative 1, I'll just leave it like that for the moment, plus c. And we're told that if we plug in 3, we get 0. So what is f of 3? I can plug that in, so I get the natural log of 3 minus 2 times 3 to the negative 1. That's 2/3 plus c, and all that's equal to 0. So I can figure out what c is. C should be, well, move the 2/3 to the other side, move the natural log of 3 to the other side, and we're good to go. This will be our answer. So f is going to be the natural log of the absolute value of x minus 2 over x, because it was 2 times x to the negative 1, plus c, which happens to be 2/3 minus the natural log of 3. It's not a pretty constant, that's for sure, but it's just a number, and we can plug that in. So, using some initial conditions, we can solve for the constant that pops out of an antiderivative. When you take an antiderivative, we get the constant, and we don't know what it is, but with a little bit more information, we can figure it out. And that's our introduction to antiderivatives.